What's up, Eigen family? How
Welcome.
you guys doing?
Welcome to another show of Eigenbros. We're going to go through all the formalities.
Mm-hmm. Yes, make sure you guys like, comment, share, and subscribe if you have not already. Also, check out our socials, eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, and Eigenbros2 on TikTok. Mm-hmm. And then, of course, patrons. We love you guys.
Yes,
we greatly appreciate the support. Thank you so much. We couldn't do it without you guys, so you guys are a huge part of this and allow us to continue to do this. And if you guys like our stuff, consider checking out patreon.com/Eigenbros, and then you can sign up, and we do a 30-minute podcast there every week, audio podcast. And we also got the Discord up now, right, Juan?
Yeah, we do. So you can, the patrons also can DM us and ask us questions. There's a lot of people that ask us advice about stuff. So
right.
Look, we've been through the physics pipeline, so we know what it's like. If you have any questions, you can always ask us on our Patreon or even our Discord. So.
Indeed. Now let's stop begging for money.
Yeah.
On to the podcast.
Yeah, on to the podcast. So today we had a topic brought up to our attention.
One of the community members, right? We had a little community post asking some topics people wanted to see. Yeah. People have some really damn good ones.
They had some. Yeah,
this is our audience. Hell yeah.
Yeah, they had some good ones. But there were some that were little short giraffes. We can't reach the high fruits just yet.
Yeah, we need some studying. There are some ones on there I definitely want to get to, but I gotta study.
Same here. I saw there's so many cool topics, but I tried to pick one that was attainable enough where we could comment on it.
Gotcha.
But still sort of technical and interesting enough that some people can get something out of this.
Okay, cool.
So,
and I'm going to get something out of this too because Juan he's the guy who knows it all.
I'm going to try. I'm not going to say that I know it all.
Or he's the one who knows more right now because I don't know anything about this topic. I have not done any research on it, so I'm a fresh pair of eyes on this one.
I'm sure you know, but as the show title suggests, we're talking about delayed choice quantum eraser experiment.
Fancy.
Yeah, made famous by Scully et al. In 1999. Yeah.
Is that Scully and others? Or?
Yeah, and others. In 1999, they published a paper. It's a derivative experiment based on Young's double slit experiment. So it looks at
derivative or it's a
it's built. I guess it's built on. Maybe it's maybe a better way to put it is it instead of having the detector at the slits, now it has the detector on the screen where you know what I mean? Does that make any sense? Because Young's double slit.
Oh, it's once it hits the screen, it also registers the state
of what
so they're trying to minimize the distance between detection and actual how would you call it? Producing the interference pattern or
because the traditional Young's double slit is there's two slits, right? And the photon goes through. But the thing is, when the detector's at the slit, it interrupts the state, right?
Yeah, it collapses the state.
Yeah, when it collapses the state, there's a screen maybe a couple meters away or whatever that detects if it's interfered with, it collapses and you get two bands, right?
Right.
But then if it doesn't interfere, then you get the spread.
Right.
You get the interference.
This is a classic for the people who may not be familiar. This is a classic quantum mechanics experiment showing that you collapse one of the first.
Probably the first.
Yeah, maybe you're right. I'm not sure.
Because that was in the 1800s.
Wow, that's crazy.
I know.
This is so funny. You don't think of that, a quantum experiment like that. That's so fundamental and such a good demonstration of quantum. You don't think of that as 1800s.
I know, but I think it is. Young is 1800s. But we didn't even think about that experiment. It kind of left people scratching their heads for a long time.
Put this on the shelf.
We'll come back to this anyway. Let's work on statistical mechanics for 100 years. And
because you told me that, and I didn't believe you. I was like, Young's double slit did not come before statistical mechanics stuff and all this, but you were right. And I was like, damn.
It does, man. We shove a lot of things we don't understand. And
But where's that now in the modern age? I guess it's dark matter and
Oh, we're shelving stuff like that?
Well, dark matter is kind of like this thing where we're just like, I don't know,
Yeah.
95% of the universe is dark matter. Well, let's just continue to do our calculations with matter because we don't know what that means.
That is true. Yeah, that's for sure going to be one of those things in like 100 years. Something's going to happen, and then we'll find some kind of loose connection to it.
Yeah.
At least that's the hope, right?
Well, hopefully sooner. I don't want to have to wait 100 years while I'm dead to see what dark matter is. I want to see that shit while I'm alive, you know? I want to see alien aircraft, or I want to see our own version of alien aircraft using dark matter
yeah. Oh,
anti-gravity.
We owe the audience a follow-up to alien stuff.
Oh, yeah.
Because there's been official reports coming out. But anyway, that's...
Anyway, yes.
We digress. But anyway, yeah, the young... It's a sort of... built on to the Young's double slit experiment, where the detector's at the slit, but in this case, the detector is farther away near the screen, and the screen. So the idea is that it's trying to see if the observer effect happens just because it's at the slits at the site, or if it's like a feature of just observing or collapsing the wave function. So,
so the thing that would pop into my mind first is that ideally you want the detector as well as the screen to register at the exact same time. So you want the measurement and the screen projection or whatever to happen at the exact same moment.
Yeah, but as we know, photons they're light. So they travel at a certain speed. So ideally, in theory, we can't, unless the screens are entangled or something.
I'm saying somehow if the screen and the detector can both register at the same time,
they would have to be entangled. But this is where the future experiments come in.
Okay.
Yeah. So I like where your head is going, because that's kind of where physicists were taking this. But so the idea is that if the detector is placed after the slit on the screen, if the screen shows an interference pattern, it's inferred the photon went through as a wave, right? So, yeah. So,
but they're saying with no detector, right? If you have an interference pattern, okay.
Yeah. But if the particle collapsed, if it collapsed into a particle, then you would get the
two bands. Yeah.
So, so that's kind of how they approach the experiment. However, in the sort of modern iteration here, I'm going to go ahead and show you a video of how they set up the experiment. It's a little bit complicated because you start getting into entanglement, and then, as you know, I think entanglement is kind of like this wooey word that people throw around a lot.
Right. People love to ascribe all kinds of things to entanglement.
I know.
Souls being entangled and.
I mean, like. Yeah, like okay. So, what is? Do you have a definition of entanglement? Because I do. I have an official.
Probably not a great one, but it's just that to keep it simple, I guess, where you have two states that depend on one another.
Yeah,
that's all I can really say.
That's a good way to put it. The definition that the Sanford Encyclopedia uses is they say it's like energy. It's a non-local correlation that happens between two space-like separated quantum systems.
Gotcha. That's more precise.
Let's unpack that a little bit.
Yeah, that's better definition because they actually invoke the word quantum and the word non-local, which is very useful to really capture what it means.
Yeah. And so non-local, for those of you that don't really know, it has to do with the fact that something is space-like separated. Meaning that no faster than light signal no signal or information can be transferred faster than the speed of light, right?
Yeah.
Yeah. So that means that, like, if Terence was on the other side of the universe, not even probably, if Terence was halfway around the Earth, no, but it's because they do these experiments on Earth. So if you were on the other side of the Earth, there's a certain time that it can take for the signal to get there.
Yeah. Like if you use the fastest means of communication, it's going to take some amount of time to get that signal to me. Yeah.
So in essence, it would say, like, if I perform the experiment and if I entangle some photon, or not even I guess
I think you should keep it simpler than that.
Okay, let's keep it simpler.
I would just say, like you were saying before, I'm on the other side of the universe. You want to send me a signal. On the other side of the universe, that could take 13 billion years to send that signal to me, right?
Yeah.
But with quantum entanglement, you won't be able to send me information, but the state will collapse instantaneously on the other side of the universe.
Yeah.
So that's non-local. A local phenomenon would be something where it happens within the very, short region in which you're operating in.
Yeah.
So like within a bubble or within a radius of the speed of light. That's a local phenomenon.
Yeah.
Anything outside of that is non-local, basically.
Exactly.
If it doesn't depend on any given time of the message or the signal to travel.
Right. And we have to define this, by the way, because how else are you going to talk about quantum mechanics if you don't know what the hell entanglement means or what the hell non-local means?
Right.
A lot of this stuff actually was fleshed out by John Bell, with famous Bell's inequalities and stuff.
Right.
Which were how would you say? I guess the Bell test, like the more famous Bell test, was done in 2015. The non-loophole one.
Oh, right. But then I heard there were even some more discrepancies there, that it's not completely non-loophole free.
Yeah.
Due to randomness or something.
Right. There was that condition. Yeah. Yeah. There's a video, by the way, we did on a channel. It's called Bell's Inequalities.
Oh, right.
An
Bell's
older Inequality. One. Yeah, it is an older one. But
I don't know if it's good, so
yeah, you have to look
with a grain of salt.
Go back to that if you want to really see where that went. But they were tested. Bell's inequalities were tested experimentally in 2015 in what's called a non-loophole configuration,
or a loophole-free Bell inequality test.
Yeah. Prior experiments had like 2 loopholes. It was the communication one, and then there was the detection loophole, which are pretty much self-descriptive.
Right.
I hope I don't have to explain it too much. But like I said, you can always go back, watch the video that we have on our channel. Namely, these Bell tests show correlations that strongly contradict like local realism. That's kind of what we mean by non-local. So
right. Well, realism, you're throwing in a new word now.
I can define it.
Okay.
Yeah. So non-locality does not allow for faster than light communication, but using the definition of realism, I'm going to again use the Stanford Encyclopedia for this. The doctrine that regularities in observed phenomena are caused by some physical reality whose existence is independent of human observers.
Right.
First, that's what realism is. Does that make sense?
Right. Meaning that if you imagine, you might be like, what the hell does that mean, really? But it's like you've probably heard the famous thing where Einstein says does the moon still exist if you look at it or not?
Yeah.
Well, in quantum mechanics, that comes into question where you assume that the moon exists if you're not looking at it.
Yeah.
And that would be like the object is real.
Yeah.
If it's non-real, then it's like the universe or the moon doesn't necessarily exist, or it's in some superposition state.
Yeah.
And only exists when you look at it.
Yeah.
So we call real. So these are like reserved words. So it's like realism may mean something else in other contexts, but in physics it has to do specifically with like quantum states and collapsing wave functions.
Yep. Yeah. And it's more important when you look at I don't know. There's like a physical kind of interpretation, especially when it comes to quantum mechanics, like you're saying. There's a definition used by a physicist. I can't remember who it's from, but it's in the same Stanford Encyclopedia. It says, one can assign a definite value to the result of impending measurement of any component of the spin of 2 correlated particles. That's the caveat that local realism holds. And what that means is you can actually tell which state, like, oh, I caused this state to collapse or something.
Right.
You know what I mean? But obviously, well, the thing is with Bell's test, it shows that the universe is non-local. Like essentially, we have to rule out local realism.
Right.
In that sense.
Right. Which is disturbing, to say the least, right?
Yeah. Well, like, sort of, I don't know. And this is what you'll see if you go ahead and look this up in videos and stuff. People are saying, oh, wow, the universe. This is kind of why I wanted to talk about this, because I saw all the comments and people were like, wow, we really live in the Matrix. And I kind of wanted to, like, kind of wanted to talk about this because there's a sort of simulation theory that kind of plays into what you were saying. Einstein's quote about the moon. Is it there? Is it not?
Right.
And my point is that some people think that the universe works kind of like a video game in some sense, right?
Right. That's the first thing that made me think of, like, you know, the whole thing that the creator, what's the guy who created Doom? I forget his name.
I don't know.
Well,
I'll put a picture up.
I think maybe it's John Carmack. Please correct me if that's wrong.
Yeah.
But the creator of Doom had this revolutionary idea to render only what's on screen, and then you kind of have the rest of the information saved away.
Yeah.
And that's kind of like how, if you think of the universe, it's like it only renders when you're looking at it, but then when you look away, it's like it's stored away somehow.
The information is like the information is there, but it's not
rendered.
Yeah.
Right. Of course, the universe works a little differently than that, but that's the first analogy that came in my mind when I first heard about the concept of local realism.
Yeah, but
or
that's
the antithesis to that.
Right, but that's what people think of. Like, people say, like, oh, at least in these experiments, because you get some sort of, I'm going to put some air quotes here, fuckery going on that looks like somebody's like fixing the game in some sense.
Right.
There's some information that's being exchanged that looks like it's retro-causal. Like, it's like, does that make any sense?
Oh, you're making me... when you start adding in causality, it breaks my mind.
But I'm saying, like, it's sort of like... it's fixing the numbers so that things play out the way they should. There's some sort of determinism here. Like... But the thing is, as we know with quantum mechanics, it's a purely stochastic, probabilistic theory.
Yeah.
Right?
Yeah.
And it's non-local, meaning, like, well, it kind of defies classical theory and our classical, like... instincts about realism, right?
Sure.
Yeah, we'll talk more about that, but...
And this is what physics always does. It's going to shit on your intuition, basically. So quantum is going to shit all over your intuition.
Yeah, and in fact, that's why people throw out the classical theory of GR, relativity in general, because quantum mechanics has been rigorously tested enough to where people are like, yeah, something's wrong with GR, not quantum mechanics.
Right, or there's some link that needs to be discovered somehow.
Right.
You know, because one of the, of course, to explain for the audience, one of the missing links between, you know, if we have a theory of everything is linking general relativity to quantum, and specifically quantum field theory.
Yeah.
So we need to figure out how to link those two. But quantum field theory is like one of the most highly successful theories ever created.
Yeah.
So people are more apt to. But I mean, GR is really successful as well. But people want to really find that link between quantum and GR by quantizing gravity somehow.
Yeah.
Because we know the fundamental universe is quantum.
Right. Yeah. And that's kind of the thing. Like, we still haven't gotten there yet, but in terms of talking namely on what we're discussing today about the delayed choice quantum eraser experiment.
Right. So how do the delayed choice quantum erasers get into this?
So I first want to show a PBS video here. I think this one's best to cover first.
But it's still pretty interesting to see what happens if we try to observe the wave function at different points in the double slit experiment. The great mystery of the experiment is that very particle-like things appear to traverse both slits simultaneously, like you might expect of a wave. Physicists love a good mystery, and so have tried very, very hard to peek to see which slit these particles actually travel through before they produce the famous interference pattern. Turns out the universe is onto us. Any experiment that determines unambiguously which slit the particle traverses destroys the interference pattern. Instead, particles land in simple clumps, one for each slit, as though they were travelling as simple particles the whole time. This is even true if you place detectors on the far side of the slits, after the wave particle thing should have already been interfering with itself. It's like the wave function is collapsing retroactively, as if the universe is saying, okay guys, the human figured out which way you went, no more funny stuff, better pretend like you were particles that whole time. But there's a huge problem with this interpretation. it's impossible to make these measurements without messing up the wave. The interference pattern happens because the waves emerging from each slit are what we call coherent, which is a fancy way of saying that the relationship between the waveforms emerging from the two slits, so the locations of peaks and valleys, is predictable and stays consistent as the waves move forward. This coherence is what allows the waves to produce the interference pattern in the first place. But when you place some device in the path of either wave, you mess with this coherence, and so affect the pattern that reaches the screen. By the way, the double slit experiment where you try to determine which slit is traversed is called a which way experiment. And if the test is done on the far side of the slits, it's called a delayed choice experiment. Physicists hate being outsmarted by the universe, so they've come up with clever ways to measure which way the particle travelled while still preserving coherence. I'm going to talk about the most famous, performed in 1999. This experiment made use of a very special type of crystal that absorbs an incoming photon and creates two new photons, each with half the energy of the original. These new photons are twins of each other. In fact, they're an entangled pair, so fundamentally connected in strange ways that we'll come back to.
So, I just kind of want to lay the foundation there.
Yeah.
Because there's another better experimental setup here, or a better picture of the actual experimental setup, and maybe that will help kind of understand the picture here of what's going on in this delayed sort of choice or delayed quantum eraser experiment.
Okay. So I guess to recap then, he was saying that the delayed choice is just the Young's double slit after the detector after the double slit.
Yeah.
That's the only difference.
Kind of like recapping what I was saying. Yeah.
Oh,
yeah.
Interesting. Okay.
So that's kind of like just the foundation of it, but it does get technical in terms of how they set up the actual experiment, which is something I'll kind of point out here in this video here. And this is something that we're probably more comfortable with because we've actually been in the experimental side of things.
Oh, so I still don't like all these halfway plates and whatnot. This is already giving me a headache looking at this.
We'll go ahead and play it here. So this is the experimental setup for the...
It begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through, and because we have no measuring device at either slit, we cannot know which slit the laser fires through until they pass through and are detected on the other side. So at each firing, it will either go through A or B. Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern, if it only came here. If we could place a measuring device at the slit, we would know the path information, but with just a result from D0, we don't know the path information. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both.
And that makes sense, right?
No, could you explain it?
Oh, that has to do with the detector, where the detector is. They're saying we don't know any information about the system, so it should show up as an interference pattern.
Okay.
Right? We make no detection, we make no official measurement.
Okay, sure.
We should just purely see an interference, right?
Okay.
Becoming the wave of possibilities it could have been, instead of one of these possibilities, if we knew the definite path information. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now,
so we'll pause here. There's another prism set up here to kind of differentiate further what the detector is going to be measuring. So there's going to be 4 detectors that we see here officially, and then the video will kind of go more into what happens or what the researchers kind of uncovered here.
Okay.
Now if the photon hits either one of these detectors, notice what happens. We obtain which path information, because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. There is no way a photon that came out of B could hit D4, and vice versa. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1 or D2, it could either have come from A or B. We can't.
Does that make sense?
I got lost there. That was a little much.
Okay, they're saying like to sort of get rid of the loophole of like knowing, like sort of like making it random at some point, right?
Right.
Because like if it goes through B, you know where it goes. Remember the A and B one?
BS?
The A and B slits, like if they converge to D0, it's purely wave. There's no information. We don't know anything.
Yeah.
But if it goes through B, then you know some information.
Yeah.
So now it's going to show bands.
Yeah.
Because you collapse into a particle state, right?
Yeah.
So it's either going to come out of D3 or D4, right? But the thing is, now they add another scrambler. They essentially randomize it again, 50-50. So now we lose path information. That makes sense?
Yeah.
Ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern, demonstrating the photon went through both slits, since we don't have definite path information. Now here is one of the important implications of this experiment about what is causing collapse. Some argue physical interaction from the detector is what is causing the collapse, but if that was the case, D1 and D2 should cause collapse every time. But that is not what happens. If a photon makes it to D1 or D2, they always display an interference pattern. Yet every time a photon hits D3 or D4, a clump pattern is formed. But the only difference is what we, the observers, know about these two stations. Because of the experiment setup, we know that if a photon hits D3, it will always be a clump pattern, showing the photon only went through one slit. If it hits D1, we know it will always be an interference pattern, showing that the photon acted in a way as if it went through both slits. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that is not what the experiment shows. We always get a clump pattern at D3 and D4 because whenever a photon hits here, we always know the path information. And we always will get an interference pattern at D1 and D2 because we can never know the actual path information. So the photon acts in a way as if it goes through both. Whereas at D3 and D4, the photon only goes through one slit because we know the path information. The particles act in a way that correlates to our knowledge. See, what causes collapse is knowledge, and knowledge requires a knower.
All right. Let's slow down here.
That's really interesting, though, because that was a misnomer I guess I kind of had even before this podcast. I thought that the collapse happened because you just measure it. As soon as you measure it, it collapses. But it's even more powerful of a statement than that. It's saying, like, there's no measurement happening in this situation at all.
Well,
it's just
except when it
showing
hits the detector.
Huh?
I guess when it hits a detector.
No, but it's showing you it's not a detector though. There's no detectors in this setup. It's
only till the end, I guess. But yeah.
Yeah, but I'm saying in this situation we have right now, it's only straight up just splitters.
Yeah.
And it's saying that even with just the splitters and no detectors, if you can determine any known state, it's always going to produce that double band pattern. Yeah. And if the state is ambiguous, then it will always produce an interference pattern, regardless of the detector. So it's all just logic, pure logic.
Yeah.
And that's really interesting. I never knew that.
Yeah. This is why one of the people were saying, like, but I think knowledge here is like a little bit of a kind of a loose word to use.
Yeah.
In this video, they do talk about, I don't know, I think the language is also a little bit loose. These are photons, but I think the video, I love the video, by the way. Inspiring philosophy.
Right.
But there's a distinction to be made about like photons. Like I think they refer to the photon as like a particle, but then you have to be careful because photons are, they have the duality of sorts anyway.
Sure. It's a wavicle.
Wavicle, yeah. So in case that didn't make sense, by the way, I'm going to show another video by PBS Spacetime to kind of follow up on this. But I wanted to, before we go to that, I wanted to say, like, it seems to me that there's some interesting thing going on here with like how information is being handled or exchanged, because it seems to be like there's a cost to knowing, to having information.
Right.
And this kind of has to do with something that we're slowly discovering in physics. There's something a lot more interesting going on about.
Yeah, it's interesting.
Yeah, I
sure.
know. But we'll have some
learning lots already in this podcast.
We'll
love it.
I'll show the other one here by PBS Spacetime, continuing how they're going to explain the experimental setup here.
Okay.
Crystal in front of the double slit to make coherent entangled pairs of any photons passing through. Send one of each pair off to the screen to produce our interference pattern, and use the other to figure out which slit the original photon passed through. Let's focus on detectors A and B here. Detector A lights up if the original photon passed through slit A, and detector B lights up for slit B. If we run this for a bunch of photons, we see that whenever detectors A or B light up, we get a simple pile of photons here at the screen. No interference pattern at all. It's as though any knowledge of which way the original photon travelled stops it from acting like a wave during its passage through the slits. And crazier, this experiment was set up so that photons reach A or B after their twins reach the screen. So, a photon lands on the screen according to the pattern defined by its wave function, and then later, its entangled partner reaches detector A or B and somehow retroactively influences the previous landing position. It's like the second photon is saying, whoa, someone figured out which slit I came through, you better look like you came through that one too. This is amazing, and given that we only interact with one of the entangled pair, surely that means we aren't messing with the other, so we aren't ruining the interference pattern with decoherence. Could it get any weirder? This is quantum mechanics, so yeah. This extra stuff is the quantum eraser. Its job is to destroy any information about the path of the photons. These devices are beam splitters, just half-silvered mirrors. They work by allowing 50% of the photons through while reflecting the other 50%. Now, you have a new possible outcome. Instead of being reflected to detectors A or B, half of the photons end up in detectors C or D. But this clever arrangement ensures that if C or D light up, we have no idea which slit that photon came from. If we only look at the photons whose twins end up at detector C or D, we do see an interference pattern. It looks like the simple act of scrambling the which way information retroactively sends the message, okay, chill, the observer lost the info of which slit we went through, it's safe to have gone through both again. Are we forced to double down on the interpretation that observation of the path causes the collapse of the wave function, and that the wave function can collapse all the way back to wherever our new knowledge extends to in the past? Some sort of retroactive reality cascade? This is a pretty wild story. For that reason, it makes sense to be cautious, even of the Copenhagen interpretation. Part of the appeal of the
mind-blowing.
You can see how people kind of get into like, bro, this is simulation.
yeah.
This is because it's wild stuff.
It seems like there's a weird tie. Now it feels really close that there's this weird tie to consciousness and quantum mechanics. Like there should be some kind of like deeper connection between consciousness and quantum mechanics.
Yeah, I mean, especially that's what I mean. Like, especially if you look at realism, right? We're supposed to be independent from the we're supposed to be independent observers, right?
Right.
But if we're having this sort of like the universe writes the information
right
as we observe it,
right,
or renders the information as we observe it,
it's almost like the universe didn't exist before anything conscious existed.
I don't know. I mean, look, of course we get into speculation, but there are different takes on this, okay? So, and I will say there's a good take by the Sanford Encyclopedia that I saw. But yeah, I mean, look, this is not something. There are quotes that I'm going to put up by Wheeler and others that I guess I can show here.
Yeah,
it's in this other video. I'll just go ahead and play them here.
Sir Rudolph Peirce said, "The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result. You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows." John Wheeler said, "It begins to look as if we ourselves, by a last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in shaping what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record in the present."
I've always called the past is not really the past. Well, he says the past has no meaning or existence, which fired like sorry, this is like a really hot take by Wheeler here.
The past
interpreting this result.
Right. He says the past has no meaning or existence. Now, what does he mean by that? I'm kind of lost in that conclusion.
Yeah, he's saying like because the quantum eraser experiment is like saying like, oh, we kind of like.
Oh, because we knew information previously.
Yeah.
But then as soon as it became scrambled.
Yeah.
Now we don't know anything about what happened beforehand.
Yeah.
Interesting.
Cold take though.
Yeah, that's an interesting. From a logical standpoint, that does make sense, but
I mean, it doesn't seem like reality to me.
Yeah,
we obviously store information,
right,
and write that information. We copy that information,
right.
So it does exist. Like, you know, I think there's like a famous quote by Feynman. He said the philosopher would die of starvation. I'm making it loose here. The philosopher would die of starvation because he's questioning the reality of his steak in front of him. Like there's like
right.
There's like
at some point just just move on with the day.
But there are certain things that are undeniable. Like like the past.
I don't know if anything's
exist.
undeniable. I think things are just conveniently undeniable with whatever your problem you're solving. Sometimes you have to ignore certain things to solve certain problems, right?
Okay.
But at the end of the day, we wouldn't be having these discussions if everything was if things were undeniable, right? We can just go layers and layers deep.
That's fair. I'm just saying, I'm looking at this quantum eraser experiment. People kind of go into the highfalutin things, like just sort of. I think it's easier to kind of look at that, and I think this is what lends into a lot of simulation theories, because it does look like a video game. It does look like this kind of thing, like where the universe. And I'll go ahead and show a little infographic of like the NPC in the video game, how they're looking at a space and it only renders the draw distance. You know what I'm saying? Yeah.
The classic example you can see is with Doom.
Right.
You know, as soon as you move the mouse, then that one side will render, and then it will continue to do that.
Yeah.
And even if you tried like programming Doom or anything like that, that's how you program it, like on calculators.
Yeah, and I mean, essentially, you can look at it as kind of like a light cone.
Yeah.
Yeah.
Well,
like I mean, if you're talking about reality, right? Like you have your own sort of perception, like light cone kind of thing. But the universe, I mean, it's only rendered what 13 point something billion years or something.
The
How
universe.
many billion light years is the radius?
The universe across is 13.8 billion.
Yeah.
Light years, I think, across. But they say that the universe could actually be bigger than that because some of that light has vanished potentially, right?
Yeah.
Because after a certain point, the inflation of the universe is faster than the speed in which the photon can actually make it to our eyes.
Yeah.
So that part of the universe could already be gone.
Yeah.
And they speculate it could be around 90 billion actually, the radius of the universe. The observable universe is 13.8 billion.
Do you think if the universe has like it's a sandbox, if it's like a sandbox video game, do you think like coming outside of it is like
it's like rendering like GTA?
Yeah, where you see the map, but it's like you're like still exist outside the map.
Right.
And you're just like woo. You know?
Oh, like you're like in no clip mode.
Yeah. Well, like what happens? Like, like, do you think that there's a do you think there's a bounds? And if there is a bounds, can you, a physical being, exist outside these bounds?
Bro, this is all metaphysical at this point. That's a philosopher's question. I mean, if I had to speculate, I think that perhaps there could be.
Because there's no forces, right? If it'd be like sort of like.
Well, I don't know. The thing is, like, let's say if out of bounds could be a whole other set of like physical laws, right? Or maybe not necessarily a whole other set, but they're just like a deeper set of physical laws, you know?
Yeah.
Like our universe, like a classic thing that people think of is the whole like multiverse theory, right?
Yeah.
Where our universe could be like a particular bubble or something.
Yeah.
And then there could be other different types of bubbles out there that render these different constants, physical constants and laws and whatnot. And maybe that's what's outside the universe. But this is all within the realm of sci-fi, basically, right?
Right.
You can't really say any of these things until we have, deeper knowledge somehow.
Yeah. Yeah, there's some retrocausality arguments to be made here, like, there's some scrubbing essentially of information. Like I think these experiments show that information is something more integral to like how we are handling physics.
Yeah, and we keep coming to this conclusion, right?
Yeah, it's like a lot
of these things we keep analyzing deeper. We keep seeing that there's some fundamental aspect to like information, and like there is kind of this weird like mathematical underpinning to the universe that's really like showing its head lately.
Yeah.
It's like the physical is now becoming less prominent, and we're analyzing these really deep, like fundamental, foundational aspects of things where it's like you can start analyzing just the logic of these things.
Yeah, it's definitely more abstract.
Yeah.
And obviously more fundamental because you're kind of removing it from that. My head's kind of been going around these kind of topics lately, but maybe we can discuss these things later. I kind of want to wrap the
part up.
The takes of some of this. Like there was one professor that said the delayed choice experiments that people are interpreting, I guess, like interpreting it wrongly. People saying that they reveal backward causation or retrocausation. This gentleman, David Ellerman, believes that there's a separation fallacy, is what he calls it.
Okay.
And I'm going to go ahead and read it. He says, "We have seen the same fallacy of interpretation in two-slit experiments. Which way, they're called which-way interferometer experiments, polarization analyzers, and Stern-Gerlach experiments. The common element in all the cases is that there's some separation apparatus that puts a particle into a certain superposition of spatially entangled, or how we would, physicists describe it, correlated eigenstates, right? Mm-hmm. In such a manner that when an appropriately spatially positioned detector induces a collapse to the eigenstate, the detector will only register one of the eigenstates. He argues that the separation fallacy is that this is misinterpreted as showing that the particle is already in that eigenstate in that position as a result of the previous separation. He says, in fact, the superposition evolves until some distinction is made that constitutes a measurement, and only then is the state reduced to an eigenstate. The quantum erasers are more elaborate versions of these simpler experiments, and a similar separation fallacy arises in that context."
Okay, I lost it a little bit.
So he's kind of saying that, like, sort of the scrambling or whatever, the things that kind of scramble the states back up. Mm-hmm. Remember, we're still in the eigenstates of the wave function, the total wave function of the initial system.
Okay.
Right? This is sort of like in the abstract, like the wave function still has that information preserved of the state.
Okay.
Does that make sense?
Yeah.
Remember, because when this time evolution of a wave function happens, over time it goes back, or it should kind of revert back to the original state, superposition.
Yeah. Okay.
He's
it's never going to go to any like completely random state. It's only going to fall into the states that are possible.
Yeah, but he's saying that the scrambling and unscrambling is something that we already know. It's not anything new, a new feature of quantum mechanics.
Right.
Like, at least that's his argument. He's saying that we're making a weird separation.
I see.
Yeah.
Okay.
He's saying it's not a bug, it's a feature.
I have to think about that one a little more, but it just sounds like you're saying like we start off with a particular quantum state with certain weights, right? Like you can be, of course, some people may be familiar, but quantum systems can be represented as these, linear combinations of states. So like for example, like you could have a state A, B, C or something that has a certain probability to collapse into those states depending on how you measure it, or just depending on what the state is, right? And when you collapse the wave function, then you collapse into a particular state, but what's happening is it's just putting that state back into superposition, but it's still that A, B, C state linear combination of those states. It's not like you're getting a new state D added to that or something.
Right.
But I don't really know how that's for me, I don't really understand what that is how that's proving retrocausality to be a wrong interpretation.
He's saying that the information of the state is sort of written. I guess the argument is that the information of the state is written retroactively. I can read a follow-up quote.
Okay, yeah.
So it argues that when one describes a system in superposition of eigenstates, it does not mean that the system is in any of these eigenstates before some measurement is carried out. Does that make sense? It does not mean that the system is in any of these eigenstates before some measurement is carried out.
Right.
So he's saying it's wrong to interpret delayed choice experiments.
I see, because it's like
as if the future determines some past eigenstate.
I get it, because he's saying like you have a superposition of states, you're measuring it, which collapses the function, but then you're re-putting it into a superposition. And it's not like that previous collapse is telling you any past information, really.
Yeah,
I see what he means.
Yeah,
but that's weird. You have to like have your quantum. You have to have your quantum helmet
Foundations,
on. Yeah. Because it's easier to analyze it when you're thinking of it in terms of like the physical math and all this stuff.
Yeah.
But then when you're actually thinking of it in real life, it's kind of fucked up. So
this is why the math is really, really useful.
Yeah.
Yeah.
That's a rule in my book: is never analyze quantum mechanics without the math.
No,
because you will screw yourself.
But that's Ellerman's point, and I respect his point. But I did want to see what PBS Spacetime had to say in closing, because I forget his name.
I think it's Mark.
Mark?
Maybe.
Mark, yeah, Mark.
Yeah,
I was gonna say something that you called him last time, but I'm not going to say.
What did I call? What did I say?
You called him like normal Mike. Peter Dinklage.
Oh. He does look like a normal Peter Dinklage, I gotta say.
Sorry, Mark, but please, if you want to come on the show, you can.
Yeah. No hate. I'm sure he's heard it before.
You're welcome. You're welcome here.
Peter Dinklage is a handsome guy.
He is a handsome guy. Mark is a handsome guy.
Yeah, I'm not throwing any shade.
No, for sure. But I do want to see what the PBS Spacetime video had to wrap up, because I wonder if they had the same take as Ellerman here. Like if this is like, if this kookiness is so can be explained with our regular knowledge. So here we go.
The Copenhagen interpretation.
And again, I forgot to unmute it.
Is that it avoids any physical interaction that moves faster than light. See, when a spread out wave function resolves itself into a set of known properties, say the location of a particle on the double slit screen, somehow the entire wave function knows to do this, to collapse at the same instant. But if these wave functions aren't physical, as the Copenhagen interpretation would tell us, then there's no real instantaneous physical interaction. By contrast, a physical interpretation of the wave function, like the de Broglie-Bohm pilot wave theory, requires an underlying physicality, a set of defined properties that evolves with the wave function, so-called hidden variables. That's a bit uncomfortable, because to explain experimental results, those physical properties need to act and change instantly at any distance. They need to have what we call non-locality. Now, the delayed choice quantum eraser double slit experiment doesn't tell us whether the wave function is physical or not.
I want to pause here because he did say something. He he made a statement that I think is kind of important. In the Copenhagen interpretation, the wave function is not real. And what he means by that is like, you look at the wave functions that we use, they're sort of like they have imaginary constants in them.
Right.
Yeah.
And we know like there's no physical meaning of an imaginary constant for a state, right?
Yeah.
That's why they have to be Hermitian.
We take the norm.
Because you'll eventually get a real result when you take the square of the wave function.
Yeah.
And then we actually have a meaning for that.
Yeah. So, and that's kind of what he meant. I just wanted to elaborate on that, but we'll keep going.
But it tells us that the Copenhagen, or any other metaphysical interpretation of the wave function, is no less, well, crazy sounding than a physical interpretation. In fact, the solution may lie in this fascinating phenomenon of quantum entanglement. As we'll see in the future, entangled particles really are able to influence each other instantaneously, and we'll see that their non-locality doesn't violate causality. So perhaps they can even affect coherence and decoherence retroactively and physically without making a causal mess. Perhaps this thing we call observation is just entanglement between the observer and the experiment. Perhaps the evolving tapestry of entanglement, in all its impossible complexity, is what really defines reality in this space-time.
Is that all, or is
there
more
all.
After? Okay.
Yeah. So you kind of ended it on like a cold.
Yeah, I was like expecting a little
nothing
more.
To say.
He's like, well, that's enough time. That should be good enough. For Audible.
I'll leave you with that question.
Yeah.
Yeah. It's what did you think about what he had to say? Like, it's sort of, it kind of ends in this weird Wigner's entanglement thing too. Like, where does it end? Where does the entanglement end?
Yeah, I think he puts it on a cliffhanger because really the whole of quantum mechanics is kind of a cliffhanger, right? We don't really know, right? If we knew what interpretation was correct in quantum mechanics, I think we might have a more definitive answer. But people are still arguing on the interpretations to this day.
Yeah.
You know, if we got many worlds is coming up, lately. But the standard seems to be the Copenhagen interpretation, which is taught in school.
We've talked about this like kind of ad nauseum, but the Everettian sort of take, which has some popular proponents.
Yeah.
I don't
likes it too, so I'm like, damn, maybe I need to look at this.
Well, the Everettian one is convenient, I think, but I don't think it. I mean, there's a lot of things that don't have to make sense, but it just seems. I don't know. The universe does seem sort of like in this way, like automated, sort of just networking kind of thing. Like it's sort of fractal nature to it. You know what I'm saying? It's got this underlying like ability to just kind of like just expand. But I think this expansion comes from some kind of like obviously some energy.
What has ability to expand? Can you be a little more clear?
Sorry, I'm thinking about the quantum systems, like, because the Everettian one is like when you're presented with the quantum system, and those choices are the choices that are made in the collapse, like you just happen to collapse into that state. So now you live in a universe where that reality where you collapsed, let's say, going back to your argument about ABC, the superposition of ABC. Let's say I ended up at B, the universe split into three. That was a node, and split into three. Like you have these nodes or whatever, and then you
only see like B because that's the one that you collapsed into.
Yeah. Which I think is like egregious because I'm like, for me, fundamentally, it's like that seems like if you're thinking about a computation, if the universe is computational, and if we think about it in terms of like, it seems to me like there's a principle of like. Everything wants to go to its lowest energy.
Right.
That doesn't seem to...
It's not really in line with the universe we know of.
Right.
Like, the universe always wants to go into low energy states, it seems. But then again, I'm like, who's to say? Because, like, maybe that's just a feature of the larger...
Macro scale?
The macro scale. And maybe that is low energy, the lowest energy state in this really crazy,
That would be...
Of course, you don't want to think like that all the time.
Occam's razor.
Yeah.
What's the simplest explanation?
Right.
Yeah.
We have to kind of almost keep it close to home because like we haven't seen anything like that, so it's not the first thought you should have. it's a thought you can have, but you need to really back that up. You should probably think of the things we know of first before you resort to that logic there.
Yeah, that's what I mean. Like, I'm just like,
Yeah, it feels like a lot of wasted energy. It's like the universe really doesn't like wasted energy, it seems.
No, and I mean, like, sort of the takeaway from this, again, is I think it doesn't really, the quantum eraser thing is not really, there's something more fundamental about information, and it does have to do with entanglement, like the PBS Spacetime video ended on. We don't have the answers because we're not quantum, what is it? People study this for
quantum philosophers.
No, this is Foundations of Quantum Mechanics, which is something that I would love to study, but there are very few people doing this kind of stuff.
The big guy I only know of is Sean Carroll. He
studies Foundations of Quantum Mechanics?
Pretty much. He always talks about that. He works with philosophers and things. I don't know. I know he's really into the philosophy of quantum mechanics, though. He's probably the biggest proponent I know of Everettian and quantum mechanics.
Yeah. Yeah. So, I mean, I don't know. I'm more aligned with I think Mythina about the de Broglie-Bohm kind of interpretation here.
No, I think Mythina was into the
she's Everettian
worlds.
too?
Yeah.
I thought she said she had. Well, she said she had a soft spot for the de Broglie.
Maybe so. I can't remember exactly.
But I don't know. I don't think the universe would allow.
I thought she didn't like the Bohmian. Hold on.
Well, you can go back.
I don't remember now.
I'll put it on the video here. But the point is that I think I don't think that you have this sort of expansion Everettian thing going on. I think it's a lot simpler than that. I think these results still align with what we know about quantum mechanics, like Ellerman was saying. It's just it's a feature of the state of the superposition that we're seeing again, so it's going to produce an interference pattern. One of the other comments on the video were about causality, like what does it mean for causality? I don't think it says anything about causality. Did you feel like you walked away from that saying like, oh, there's something to say, like what Wheeler was saying?
Well, the only thing I can't really say if it says anything about causality besides the fact that we need to understand it a lot better. Because we do have these weird non-local phenomenon that somehow do not violate causality because of things like what we were talking about before with information.
Right.
Like there's no information that travels in these entangled systems.
Yeah.
At least not that we know of yet.
Right.
But at least the logic would hold in these, the causality holds if you cannot transfer information somehow. And then the fact that we also get these weird, interference and, collapsed patterns when you understand information or not. So to me, more than causality, it tells you something about information. Like information is this critical piece of the puzzle we need to understand better.
Yeah.
And maybe then you can tie that together with causality once you understand information better. But for now, I would be reluctant to say anything about causality.
Yeah.
That's when you start to, when you're talking about causality, I think is when you're thinking of quantum mechanics in the terms of this physical intuition picture, which is no. You don't do that in quantum.
Right.
Think of the mathematical picture.
Yeah. That's what I'm saying. And here's the thing about taking classical thoughts in the quantum regime. Bell's test and Bell's theorem kind of shows you that you can't think about causality in a quantum system.
Exactly.
Yeah.
This is a failure of quantum mechanics. People have not learned yet. Stop thinking about quantum mechanics in this physical, this physical classical intuition framework.
Yeah.
Because we are humans. We are not built to think like this.
Yeah.
Follow the math. I even have to remind myself of this. I'm like, I start to get convinced of these things. Like, oh shit, like, damn, he's right. There's retrograde causality of these things. It's like, no, you have to like wipe your brain like sketch. Remember that quantum mechanics. Just think of the math.
It's a different beast.
Only think of the math. You're gonna always screw yourself when you use your intuition. It doesn't work with this.
That regime. Yeah, that's.
It's the fundamentals of reality that we're not used to dealing with. Like humans are not built for this. So we have to use the tools that we have built to think in that regime because those are the effective tools for that.
Yeah, kind of going on to this writing or piggybacking the information thing. Do you think there's something like if we're talking about a field theory, right? If there's something that permeates all of space-time, I guess, right?
Yeah.
Permeates everything. if this sort of, like, I think about information in the sense that, like, okay, a particle can feel. We know that a charged particle is felt all over the universe because it falls off 1/r², right?
Yeah. Well,
and it never goes to
eventually
zero.
be held. It will eventually be felt
It can,
all over the universe.
Right.
As
it doesn't
long as
approach zero. It's very small, but it's still.
It approaches zero.
It approaches zero, but
Yeah.
I'm saying it's still a part. The universe still feels that.
Yeah.
Charge.
Once it catches up.
Yeah.
Because of course, charge propagation, the electromagnetic force is a local thing, a local phenomenon,
Yeah.
and it propagates. It takes
With
time
the speed
to
of
propagate.
light. Yeah. But the thing is, like, what's interesting about these entanglement sort of systems is when we're talking about quantum spin, we're talking about angular energy.
Momentum.
Yeah, angular momentum, angular energy here that's being exchanged, like quantum numbers of angular, phenomena, right? Like quantum numbers L and S. You know what I'm saying?
What about them?
I'm saying that there's a sort of conservation. There's already a conservation principle that we're all familiar with, and it's conservation of energy, right? And it says something about, like, if these two spins are correlated over space-like separation, and, like, the information exchange is only important to us, but the particle knows, or the state of the entangled particles are sort of.
They're entangled.
They're entangled. Yeah, damn it. It's hard to escape you don't have the language for it.
They're correlated, I guess, maybe.
They're correlated systems.
But correlated is a little bit weaker than saying entangled, because entangled implies that they have this instantaneous connection. When one is affected, the other's affected.
Yeah. And yeah, that's the right take to have.
Yeah.
But I'm saying, like, people often wonder, like, what is there information? It's how does the particle know the information is exchanged?
Right. And that's the thing is, there's like this weird.
Well, there's a cost
connection.
for us, but there doesn't seem to be a cost for the particle.
Yeah, the particle somehow knows. We need to find out how to get that information the particle knows. If we could somehow figure that out, then I think that would be a crazy discovery. I don't even know if that's possible.
But I think it's sort of like this thing where it's like a whack-a-mole thing. Not a whack-a-mole thing. It's probably better yet put like how when water beds were super huge.
Yeah.
It's like you push down and then the other part kind of goes up.
Right.
It's like it's this sort of continuum of, like, even though you're far away, like, you know what I mean? Like, it's
but if you're thinking of in terms of that still feels
speed
local,
of water.
because we're still using our bad human intuition, right?
Yeah.
We can't conceive of a non-local thing. I mean, we can conceive of something that happens instantaneously, but it's like for causality to be preserved, we can't really think of how that would make sense.
Especially with what we know about how space-time behaves.
Yeah.
Yeah.
I think the more you learn, actually, it becomes harder to think in that way. Like, I can only really imagine local things that make sense. A non-local thing, I can't really make sense of that, especially when you're thinking in terms of relativity and whatnot, and
Yeah.
it starts to get messed up then.
Yeah. Well, I've been thinking a lot about foundations of quantum mechanics. And one of the things I've been thinking about GR and quantum is sort of like the duality of sorts, like space and time, and then particle wave kind of stuff. And I was like, I think if we're to take quantum mechanics as, like, what is true, is there something in quantum, like, in the postulate of quantum mechanics, like, the one thing that we scratch our heads about is the act of measuring. That is the one thing that we're still all, like, scrambling our heads about.
Well, it seems like measurement can be thrown away now. It's just a matter of the logic now, because with this delayed choice, it shows you don't even need to measure the state.
What do you mean?
It's just all about looking at the interference pattern. The measurement almost is like a red herring in some sense, because it makes you think that there's more power to the measurement than there is.
No, but the measurement act is like you go from. It's a non-linear process, meaning that, like, you can't just go from this state to this. Like, you can't just choose the state in some sense. Does that make any sense?
Oh yeah, sure.
Yeah.
You collapse the state just by hitting it, let's say.
Yeah.
Or tapping the state.
Yeah.
But to me, I don't even like the measurement now, because the delayed choice shows you that the measurement is not even important to the picture of interference patterns and otherwise.
Okay.
So measurement almost and looking at this stuff is kind of like, that's what I'm saying. It's kind of a red herring. It's like it adds more confusion actually than this even more beautiful, pure experiment of delayed choice.
That's interesting.
Because it's like it shows you that really it's all about just the weird information, information aspects somehow, or just like this. It's all about the entanglement now, showing that the superposition exists whether you measure the state or not. You know, and then the collapse will exist whether or not you measure as well. It's just all about the logical sequence of how this particle moves.
Yeah, I'm thinking there's something more. Probably the most fundamental thing we can talk about is entanglement.
Right. There's something very fundamental there for sure.
Yeah. Like, I wonder if gravity, like, because, like, if that's the most unique feature of quantum mechanics, like, I wonder if, like, the answer of gravity lies somewhere in there, like.
Perhaps.
Just, like.
It would make sense to lie within the regimes we don't really understand.
Right, that's what I'm saying. Right? Yeah, like, because we're looking at things that we try to do understand, not looking at things we don't understand.
Right. The number one fallacy people make, they think using the same equations and things is going to somehow get you the new answer, but sometimes it requires a leap of really new insight.
Yeah. So I wonder if gravity is sort of, again, like a misnomer, like you were saying, a red herring sort of.
Gravity itself?
Yeah. Like maybe it's an aspect of something. Maybe it's an aspect of quantum mechanics.
Oh, perhaps. Well, people have already tried this with graviton, at least.
Well, I don't know. Yeah, particles, I guess, are kind of the easy way out.
You're like particle zoo.
No, because that's the thing. That's the first thing we go to when I thought about, like, oh, there's got the particles exchanging information. Maybe they're exchanging particles.
Yeah, a gauge particle of a graviton.
Something.
Right. It's a classic example, but
we know that
signals.
But we know signals. You know, it takes time. If you go to the speed of light, yeah.
But actually, there was an interesting quantum magazine article, and it was actually one of the suggestions in the community post again about a 2D version of quantum field theory was able to square away with GR, I think, or something like this.
You mean string theory?
It might be. I think it might be related. I'm not sure.
Yeah, or maybe it's like a new formulation or something.
Yeah, mathematicians found some 2D theory. I don't even know what it really means. I'm just trying to recite the article name.
No, strings are one-dimensional. I'm tripping.
Yeah, I don't know.
Yeah.
Whatever it is, there's some 2D version. Some mathematicians found some 2D quantum field theory, something or another, that can square with GR. I'm probably fucking this all up, but whatever. I mean, go check out Quantum Magazine article, and you can look at it, but
we'll post.
It seemed interesting. I didn't get to read it because I've been too busy, but maybe one day we can do a podcast on it.
Yeah. But anyway, folks, we hope you found something useful on this. We hope we kind of elaborated on some of the physics woo-ha that's out there, and like
woo-ha.
Yeah, just like
sound too close to Wuhan.
Oh no, sorry. Yeah, no, I'm gonna bleep what you said because
we get demonetized for that still.
No, I don't know. I'm just saying. I'm just being cautious.
Be proactive.
Yeah.
Gotcha.
But anyway, don't forget to like, comment, share, subscribe.
Indeed. Check out Eigenbros.com, Eigenbros Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then once again, thank you patrons. We greatly appreciate it, guys. And if you want to sign up for Patreon, check us out, patreon.com/Eigenbros. You know, donate $1, get a free audio, or I guess not free, but get an audio podcast, 30-minute audio podcast every week where we talk about random stuff, me and Juan. And I think that's it, right, Juan?
Yep.
Okay.
That's it.
Okie dokie.
Folks. We'll see you
later, guys.
Peace.